Chapter 8 here is about gases, and I believe I've mentioned before that I absolutely love the elements of the periodic table, and it's probably my favorite topic in all of chemistry, and if we could spend the whole class focused on that, I would. However, after that, gases are probably my favorite topic next. And part of that is I feel like the gas laws are fairly simple and easy to understand, and that's in part because gases are really where chemistry kind of got its start. Like there's this old idea of alchemy with the 4 elements that Plato theorized that were around, maybe 5 with the spirit in there, but earth, air, fire, and water, and that everything was made up of those. Well, of course, air would be gases, and he kind of identified states of matter there, but he didn't identify elements by any stretch. And it was alchemists who were trying to turn base metals like lead into gold, and who are trying to make an elixir of life and a potion that make you stay alive forever. And they thought the same chemical could do both of those, which is strange. There's reasons why, and their logic kind of makes sense if there were actually 4 elements. But it was alchemists at least, who were studying these things, who began to kind of find flaws with it. That it turns out you could take water and you could break it into 2 gases, and one of them helped things to burn, and the other one itself burned and could catch on fire, even explode. And so that was strange, because water is supposed to be this thing that other things are made up of. It's not supposed to be made up of other things. And so that was one of many experiments that began to convince these early chemists, and you'll get to hear all their names because they all have gas laws named after them, or at least many of them do. They began studying gases, and gases really is where the science of chemistry began to break away from the pseudoscience of alchemy. And so I really think that gases are simple to understand, because it's really where we got our start in chemistry. And as we've learned more, of course, we're learning the more difficult stuff. We're discovering the more difficult stuff nowadays. But the early stuff that we discovered was the simple stuff. Beyond that, though, I think they're easy. The math is easier here, I think, than some of the other topics, and I just really enjoy them. So with that, let's dive into section 1 here on gases. First, we're going to start with the properties. So this here describes us as living at the bottom of a sea of air, and sure enough, we do. And that air is made up of different gases. Your main one is nitrogen. And you've heard before, of course, that we breathe in oxygen and breathe out carbon dioxide. And that's not wrong, but it is incomplete. The air is mostly nitrogen. So when you breathe in, most of what you breathe in is nitrogen gas. And when you breathe out, you also breathe out that nitrogen gas. Your body doesn't need it, which is why we don't talk about that being what you breathe in and out. All of the bits of nitrogen you breathe in are also all the bits of nitrogen you breathe out. And so there's not a change there in the percentage, the proportion makeup. What you breathe in, though, is roughly 21% oxygen, and what you breathe out is lower in a percentage in oxygen and higher in a percentage of carbon dioxide. I'll also state that this is a little bit oversimplified. Water vapor is drastically variable, especially in the lower atmosphere. And you'll notice if you do the math here that we have only about 1% stuff that's not nitrogen and oxygen in our atmosphere currently. And to be super clear, despite being there in low quantities, carbon dioxide, water vapor, methane, and a handful of other greenhouse gases, even though they're up there in really tiny quantities, are really having a drastic effect on our environment. And I'm sorry that that's become a political issue, and if you disagree with this, I'd encourage you to look into the science of it. Unfortunately, climate change does seem to be a real thing, and we've got to make some changes if we're going to survive. And for those of you who are live in class, don't hesitate to ask me questions. I'd love to discuss this more. It's something that I care deeply about, even though it doesn't really touch on the sciences I cover quite so directly. In understanding gases, we have something called the kinetic molecular theory, or sometimes these are described as the properties of an ideal gas. And you can hear within that there's some skepticism that there are such a thing as non-ideal gases. And most gases are not ideal. They don't behave exactly like this. However, these are really safe assumptions. Now, when you're getting into a lab and I ask you what are some possible sources of error, these assumptions that we are making are possible sources of error for your lab. And all gases are actually real gases, and the math is a little bit uglier if you're dealing with a real gas. But at normal conditions, your average room temperature, your average atmospheric pressure, these are really safe assumptions. They are pretty true. Anyway, gases consist of small particles. In fact, the idea really is that they are so small that they are point particles, we can just ignore their actual size, that gases themselves don't really have significant size, that they move rapidly in straight lines. And that may seem okay, it's bouncing around inside the container, that makes sense. But in reality, objects are affected by gravity, and they tend to follow parabolas, arcs, and curves. And it turns out that the straight line that they follow here is straight enough, that the gravity does not have a significant effect on something that is that lightweight and moving around as fast as they are, the rapidly there. And it turns out that rapidly there is related to temperature. We mentioned it before, but temperature is really just an average kinetic energy. And that is how fast they're moving. It's a kinetic energy. The formula for it is 1/2 mv squared. And so the gas has a certain mass and a certain velocity, how fast it's moving around. But it's a high velocity. The heavier the gas, the slower it's going. That's something called Graham's law, which is one of the gas laws we're not going to get into here on this topic. That they have essentially no attractive or repulsive forces. That is, that the gases aren't attracted to one another. And most gases are actually nonpolar. And so that's not too big of a concern. Certainly your noble gases are nonpolar. Any gas like O2 and N2 that are bonded to themselves are nonpolar. Carbon dioxide is polar, and that means it's going to have a slight charge there, and that's going to result in a slight attractiveness or repulsiveness with other particles. The gas particles are very far apart. Unfortunately, if we zoom in to the point where we could see atoms, which of course we can't actually do easily here, certainly we can't do it for gases, then the sizes look huge, and the distances look small, but that they are spread out in very small, far apart. That the gas themselves, as I said, are small particles, that they have small volumes for the particle compared to the volume that they occupy. The gas molecule itself is tiny compared to the container that it's in. And I've kind of already mentioned it here with the rapidly, but that the kinetic energy is related to the temperature. That as the temperature goes up, they start moving faster. From here, we're going to have a decent amount of calculations to do, and those calculations are going to use these abbreviations, but they are properties of a gas, different properties that we can measure. And these properties matter because, unfortunately, gases can change size. If you think back to when we covered states of matter, solids have a fixed volume and a fixed shape. Liquids have a fixed volume but an unfixed shape, take on the shape of their container. Gases don't have a fixed volume or a fixed shape, and because of that, we can change their volume, how much space they take up, by changing the conditions around them. So those properties are pressure, volume, temperature, and amount. An amount is usually done in moles. However, we can, as you know, turn moles into grams. And so there's a kind of extra step there if you're doing that calculation. As it mentions here, if you're doing a calculation, the units have to be in moles and not in grams. And we've mentioned that before. It's true elsewhere. It's very true here. We've mentioned before that temperatures have to be in Kelvin. And that is true. It is absolutely required for calculations. Anytime you're given a temperature in Celsius, you should think I need to get that into Kelvin. We've said that before with grams as well. With mass in grams, you need to get that into moles. Volume, for most of our calculations, is going to be liters. We can, of course, convert to milliliters, use milliliters. Pressure, you will notice there are a ton of units here. And the reason there's so many units for pressure here goes back to gases were one of the first things that were studied. And so different people came up with different measuring systems for measuring the amount of gas. And unfortunately, they have persisted to today. And on occasion, someone was like, we need a new unit. We need one that everyone agrees on. And then we just have another unit to work with. No one gets rid of their old unit that they love. And so you'll hear barometric pressure on the weather report. And that one's actually in inches of mercury, which is related to this millimeters of mercury. And there are all sorts of other barometric pressures, different ways to measure air pressure out there. And we're going to get into each of those properties on the following slides. So volume is simply the space it takes up, and we assume that it is the volume of the container. And this one down here just annoys me. We're getting into the gas laws later on, and they only mention one of the things related to the gas here. We'll get to the details of that, and there's more to elaborate on that later on. Temperature, as we've said, is a measure of the average kinetic energy, and it's measured in Kelvin. And when we change the temperature, then the molecules collide with the sides of the container less often, collide with one another more often, and those collisions have an effect on pressure and or volume. Again, we'll get to the gas laws, the details of this later on. Pressure is a measure of how hard the gas is pressing against the container. And so that pressure comes in many different units. Millimeters of mercury, which is exactly equal to torr. It's just another way to write millimeters of mercury. Atmospheres. And pascals is a fairly tiny unit, so we end up having a lot of pascals, so kilopascals tend to be the preferred one. PSI, pounds per square inch, that's what your car tires will have on them, although usually there's a metric label as well, and I think most often the metric's in kilopascals, but any air compressor pump that you're using to inflate a tire is going to be measuring in PSI here in the States. Having said that, weather, we don't measure in PSI. As I mentioned, we measure it in one that is related to this, which is inches of mercury instead. Air pressure is measured with a barometer, and there's different types of barometers out here. This is your classic example and really explains where the distance of mercury measurement comes from. This was invented by Sully, whom the unit torr is named after. But you have a tube, and one end of the tube is open, and the other end here is closed. And so then the tube has a vacuum in there, and that vacuum means there's no space, nothing in there. And so what happens is the mouth of this tube is underneath the mercury level, and as the atmosphere pushes down more on the mercury, then the mercury gets pushed up the tube, and you measure the height of the mercury from the liquid layer here to the top of the tube there. If the atmosphere is pressing down less, you have a low air pressure air system in there, then because the atmosphere is pressing down less, then the gas sinks down, and with gravity, of course, there. And if the air pressure is higher, then the gas rises. And it turns out that when you have at sea level, which is where we say we have just this column of air above us, you have 1 atmosphere of pressure, and it turns out that the mercury goes 760 millimeters high there. There were water barometers like this. Water is so less dense that you needed something like 32 feet of it. And so you needed a column that was 32 feet tall, and that just becomes impractical. Meter tall is decently long. You're talking more than 2 feet here, about 2.5 feet for 760 millimeters. And so this is still a decently tall device, but at least is one way to measure pressure. We have other barometers now, plenty that are much smaller or even electrical in nature, but it at least explains where the units came from and the basic idea of air pressure. Air pressure comes from the weight of the atmosphere above you. If you have gone up in altitude, especially if you do so rapidly like you might in an airplane or driving through a hilly mountainous region, your ears need to pop. That's because your body, the internal air pressure, has to resist atmospheric pressure. And so you have all this atmosphere weighing down on you and you don't feel it. It's 14.7 pounds per square inch. Oh, I left off my pounds units there. That is a bowling ball, a heavy bowling ball on every square inch of your body. And you don't feel it because your body naturally pushes back out. And so instead, what happens is when the atmospheric pressure changes, then you station tubes in your ears. There's a few other places where your body balances air pressure, but they allow air to come in and out and equalize the pressure. Well, your feeling of your ears need to pop. If they're filled with fluid, then the air inside is pushing more than the air outside, and it wants to get out, and it's having trouble getting out. That's what causes that ear pain. The less atmosphere you have above you, then the less the air pressure is. As I mentioned already, there's lots of different units for pressure. So we define 1 atmosphere of pressure as what it is on a good weather day at sea level. Then we say you have 1 atmosphere above you. Unfortunately, the atmosphere gets thinner and thinner and thinner as you go up. So there's not actually an end to the atmosphere. And as you change elevation, then you now have some of the atmosphere underneath of you. And so there's less air above you pushing down on you. With air pressure, you've heard of high and low pressure systems. It feels weird to write those both in red because on a weather map, the L is usually in blue. And so the high and low air pressure systems change the amount of air that's above you, and it has to do with whether air is rising or sinking through the atmosphere, and that causes changes in pressure, which cause your changes in weather. As a side note, high means happy weather and low means lousy weather, and so now you know a little bit about understanding a weather map, and then your fronts are where you have 2 different air masses meeting and cold air or warm air coming in. And usually right along those fronts are where you have your precipitation, but this isn't earth science, so we probably should move back into the chemistry. But you have 1 atmosphere above you at sea level. And then there's all these other measurement scales that we compare to those. Well, you'll notice these two here are the same scale. They're just measuring in different units. They're exactly the same. The spacing is the same. It's just 2 different words for the same thing. To be honest, to me, millimeters of mercury, torr, are the same thing. Inches of mercury is just the English equivalent of that. Pounds per square inch is another English measurement. That's your PSI. Pascals and kilopascals, you'll notice the number is the same here. The difference is a comma versus a decimal because there's 1,000 pascals in 1 kilopascal. And so you can imagine that to be a conversion factor. In fact, all of these, because they're all equivalent to one another, all of those are equal to one another, and any one of them can be used to convert one air pressure into another. And so, unfortunately, there's lots of different units here. By far, the most common ones for us to use here in chemistry are metric ones, and atmospheres is hands down the easiest, because mathematically it's 1 atmosphere of pressure. Having said that, millimeters of mercury are kind of the same thing, and then kilopascals, despite kilopascals and pascals being the same thing. Those are the ones you tend to see most often, that you'll get most familiar with as you do practice problems, homework, test, etc. So, as I mentioned already, variations in weather cause different amounts of pressure, and we talk about the barometer rising or falling. That's the mercury rising or falling originally, and then as it got put into dial barometers, we describe it the same way, increasing and decreasing. It has an effect on whether the weather is going to be good or bad. You can read the details there if you want. Here we're asked to do 2 conversions then. So 475 millimeters of mercury. Well, we want to cancel out millimeters of mercury, so that goes in the denominator here. We want to get into atmospheres, which is ATM up here. The nice thing with atmospheres is the number is 1. Millimeters of mercury, you'd need that chart, but it's 760 millimeters of mercury. And when you punch that into a calculator, that is 0.625 atmospheres, which is B. Beyond that, just looking at this, 1 atmosphere, 700 millimeters of mercury, the 760 millimeters is greater than the 475 here. And so you know it's not the same as atmospheres. You know that since the pressure we're working with is less than the normal pressure for millimeters of mercury, it's got to be less than 1 atmosphere. And A and C are both more than 1 atmosphere. We could use the same kind of logic here, that 2 atmospheres is not going to be 2 millimeters of mercury. And we do know that it's going to be more, so we're going to have to do a calculation to figure out which of those 2 it is. Anyway, 2 atmospheres. And we're just doing the reverse of this one up here. So we're going to have atmospheres on the bottom and millimeters of mercury on the top. That's 760 in the numerator, 1 in the denominator. And so then that's going to come out to be the 1520 millimeters of mercury, choice B. Here, a little bit more practice to wrap up this section. The downward pressure of mercury on a barometer is equal to, the same as, the pressure in atmospheres. And a water barometer is 13.6 times taller than a mercury barometer. Mercury, you can see here, has a density of 13.6 grams per milliliter, and so then water, you hopefully recall, it has a density, although I don't like using D for an abbreviation for density, of 1 gram per milliliter. In fact, water was originally our basis of the metric system, so a lot of it is 1. Water is way less dense than mercury. Anyway, that finishes section 1.